So on Wednesday, we learned that we could work backwards. And when we work backwards from 2x, because the derivative of x squared is 2x, that's fairly easy. But we always have this plus c, because there could be a number, any number there, because when you take the derivative of any number by itself, it's 0. Now, there will be some questions where we actually want to solve for c. So we'll be given information like this. Find f of x, given that the derivative is 3x, and then you know an extra piece of information that the original graph passes through the point 2, 12. So as our starting point, we could work backwards and say, well, I would add 1 to the exponent and divide by that exponent to do my integral, and I would have a plus c. But now, if I want to solve for c, I know that when x is 2, y is 12. So it's a matter of, okay, I can plug in 2 for x, I can plug in 12, for y, 2 for x, and now it's just a matter of solving this. So we get 24, no, we can do that, let's do this. 12 equals 3 times 2 squared is 12, divided by 2 is 6 plus c. C is equal to 6. And now we can write the actual equation, f of x is 3/2 x squared plus 6. So usually the extra piece of information is they tell you something about the original curve, like a point is on it. What we just have to be prepared for is having the same question asked in slightly different ways. So on this one, it tells us the gradient. Again, that's another word for slope. The slope of a curve at the point x comma y is 16x cubed minus 3 over x to the 4. What are they telling us? They're telling us about the tangent, the slope of the curve at that point. That's the slope of the tangent at that point, so that's our derivative. So the first part was just a way of telling us this is the derivative. I'm going to change that x to the 4 in the denominator to an x to the negative 4. If we wanted to work backwards, and again, I hope you're getting used to this technique where you add 1 to the exponent, don't even worry about the number in front, and then divide by your new exponent. Even though this would probably be one you could have done in your head easily, this method just is nice and smooth. Same thing here. Add 1 to the exponent. So now we know it passes through 1, 4. So we can plug in 4 for y. We can plug in Are you okay from here to here? I did a little bit of mental math. First of all, I simplified the negative 3 divided by negative 3. That made the positive. Then I thought of that x to the negative 3 as an x cubed on the bottom. So when I plugged my 1 in, I plugged in 1 cubed on the bottom of my fraction. Simplifying this gives us 4 equals 4 plus 1 plus c. Moving everything over to the other side, c is equal to negative 1. So our final equation, 4x to the 4 plus 1 over x cubed minus 1. And we we can take this a step further and imagine we started with the second derivative and had to work our way all the way back to the original equation. So in order to do that, we would need information to solve for working backwards the derivative, and then information for working backwards from the derivative to the original function. And the reason that I have solving for d and c is we always add plus c, but if we do it twice in the same question, we should use a different letter, because there are going to be different numbers in the derivative equation and a different number in the actual equation. So if I have the second derivative is 12x minus 2, I could work backwards, right? I could integrate and get 12x squared divided by 2 minus 2x plus c to get my derivative. Now, I would need to solve for c. In order to solve for c, I need some information about the derivative. And in this question it says the point 213 lies on the curve. Well, that's on the original graph, not on the derivative. And the gradient of the curve at the point P is 23. This sentence right here, or this, it's not a full sentence, but this part of that sentence right there tells us when x is equal to 2, because it's at the point P, dy dx is equal to 23. This is going to be important because I can plug that information into my derivative equation I just found, and I can solve for c. So I can plug in 23 for the slope. I can plug in 2 for x. And I can solve for c, which allows me to say that my derivative equation is 6x squared minus 2x plus 3. And now to find my original equation, I'm going to have to integrate again. Add one of the exponents. And divide. And here, since we use c already, we have to use a different line. You're going to be wanting to just use c again, but we already solved, in a question like this, we already solved for c, and c only has one value. It has to equal 3. So if we use c again, we're saying that it would have to equal 3 again, so we just use another line. Now we're given that this passes through the point 2, 13. If it passes through a point, that's your original equation, goes through that. So we can plug in 13 for y. And 2 for x. And we can solve for our original equation. So this is the basic idea of how do you find an actual equation working backwards. Because when you work backwards, there's always, and the reason it's called an indefinite integral is because that plus c makes it not quite definite. We're not quite sure what it is exactly. To find the exact equation, you would need some more information so you could solve for that c or that e. The ones we did here were relatively straightforward. They told us very nice information. What do you expect as you get into more complicated questions? Sometimes they don't tell you quite enough information. Sometimes they tell you something that you have two things you can't solve for. Often these kind of questions get systems of equations built into them. Systems of equations, as a reminder, it's like you have two things you don't know, then you need two equations before you can solve those. So there's some questions here in your homework. We're going to do those maybe a little bit later.